All right, I'm going to be reviewing questions 11 through 21 on the recent dynamics, relatively recent dynamics quiz. So you guys have a chance to better understand ones that you may have gotten wrong. All right, let's look at number 11. We see an inclined plane and a block. It's placed on this inclined plane and it remains stationary, not moving. The student claims that the block remains stationary because as gravity tries to pull the block down the ramp, with a force equal to mg sine theta, the block exerts an equal and opposite force on itself up the ramp. Is the student's claim correct? First, we should talk a little bit about this idea of exerting a force on yourself. Some teachers will just say it's not possible. You cannot exert a force on yourself. We know that's not true. I can certainly push on my elbow right now and push on my leg and feel it. It's a force. I can certainly punch myself in the eye, which I definitely wouldn't do. But if I did, I could leave myself a black eye, give myself a black eye, and that would be evidence that I put a force on myself. So we know that just generally saying you can't put on force on yourself is not true. Sadly, I think that's part of what they said here. You cannot exert a force on yourself. It's poor wording. Unfortunate. That's totally incorrect. You can. What they really mean is you cannot exert a net force on yourself. And let's talk about that. Let's imagine that you are standing and trying to push on your waist. So you're literally just trying to take your hand and push yourself across the room. Now, can you exert a force on your waist? Of course you can. But when you do, your waist will exert a force back on your hand because that's what Newton's third law says. All forces come in pairs. Both objects will feel equal amounts of force, but in opposite direction. Therefore, your waist, again, will feel a force in this direction. This is your waist area, let's just say. Force on waist. However, the hand that's sitting over here, if this was your hand, the hand would feel a backwards force in equal magnitude, and that's very messy. I'm sorry for that. Let's make this one a little bit shorter. We don't have a lot of room over there. But this force over here would be equal. This would be the force on the hand from the waist, right? And the question would be, what is the net of those two? What is the net force? What is the amount of unbalanced force? None. They'll be equal in amount and magnitude and quantity, but opposite direction. There's no net force. What's needed to move something is a net force. If it's not moving, an object will remain not moving. An object at rest stays at rest until there's a net force on it. Pushing on yourself will never create a net force because wherever you push, that space in your body will push back on the part of your body that's doing the push in the opposite direction with an equal amount of force, and they'll always cancel. It can never cause translational motion. Translational motion is the idea that you can be moved from one spot to another spot. So if you were able to do that, like I was just drawing up, and you're standing here and you want to literally push yourself across the room over to here, that's considered translational motion because your center of mass, and you'll know that something is moving translationally as if the center of mass physically moves. I know we haven't talked a lot about center of mass because that's not until the rotation unit. But know that there is a spot in the middle, usually in the middle of most objects. And if it was a stick, for example, the center of mass is here. And that's the spot that you know that you can balance something. That's the idea. If you put the fulcrum at the center of mass and it balances, then that tells you that that's the center of mass area. It's not always in the center of the mass, by the way. If you had a baseball bat where more of the mass is on this left side, then the center of mass actually might be somewhere over here. If you try to put that on the table and balance it, you'd actually have to put the fulcrum more to the left. So it's not always in the center. But anyways, the bottom line is, in order for the center of mass of any object to move translationally, meaning from one point in space to another point in space, a net force has to be present. And the only way you can get a net force is certainly not by pushing on yourself, but by pushing on an external object. When we walk, that works fine. Right? Because when we walk, if this is your foot, when you're walking in this direction, of course, your foot is trying to put a force of friction technically on the earth It's a frictional force between your shoes and the earth, and the earth responds by pushing on your feet with also a frictional force on your feet, and that propels you forward. That's an external object. The earth is not internal to you. The earth is external to you. It's two separate objects. You can push, certainly, on an external object, and it will push back on you, and it can cause you to move translationally. And these, by the way, would be called an action-reaction pair. Action-reaction pair is the idea that when something causes contact, like your foot would be the action on the earth, the reaction is the earth back on your foot. They're a pair because they'll always be equal in magnitude but opposite in direction. That's Newton's third law. Newton's third law is all about action-reaction pairs. So external forces, external to anything, can certainly cause translational motion. Back to the problem, which is saying that the student claims that this is not moving down the ramp because it's exerting a force on itself, preventing itself from moving up the ramp, is simply not true. We know that the only thing that's actually up the ramp is the frictional force. It's the static frictional force, but that doesn't come from the block. It comes from the incline, the area right in here. That force from the frictional force from the incline is up the ramp. Happens to be equal to mg sine theta, which is the Earth's gravity force pulling it down the ramp along that axis. Those details are not necessary, but this is the correct answer. It doesn't move down the ramp because Newton's third law states that a block cannot exert a, oops, they should have the word net force on itself. Take that back. This is okay to have this. Because a block can't really move around like with it doesn't have arms. So I guess, yeah, a thing that's not alive, I suppose that's true, can never put a force on itself. We can, you know, because we have the ability to move our different parts and we can put forces on ourselves. So I guess I take that back. I thought this was originally mistyped, but now I think about it, it's fine. Anyways, D is the answer. All right, 12. Students connect a spring scale on a rough horizontal surface. The students use the spring scale to measure the magnitude of the horizontal force needed to pull the block at a constant speed. Let's just stop and talk about that for a minute. Pulling a block at a constant speed can only happen if there's friction present. Because if you are pulling a block and there was no force of friction, of course, these normal force and gravity force cancel, and those are not of interest. But if you were pulling a force, pulling a block forward with a force, and there was no frictional force, then it'd have to be unbalanced, and it'd have to accelerate. If they ever claim that something's moving with a constant speed, there must be some resistive forces, and therefore it must be a frictional effect. And we know that that's true. If you are dragging something at a constant speed, you are pulling it forward with a force that happens to be exactly equal to the sliding friction force in the opposite direction. And the vector sum of this force and this force are 0 because they're equal in amount but opposite direction. I mean, you can pull stronger than the friction force and have more forward force than backwards force, and it will accelerate, of course. Or it could be a block that's slowing down, like you just pushed it across the room and it's sliding and then it stops, in which case there's technically no forward force. There's all backwards force. It's unbalanced in the backwards direction. It slows down and stops. But know that in this scenario, and they can give a lot of different problems about this question, about pulling something at a constant speed, know that this is the details. The forward force is equal to the backwards force, which, by the way, this is equal to mu k times the normal force, right? As a reminder, which is equal to mg. So the frictional force is technically mu k times m times g. If they happen to give you information about F naught, since those are equal in amount, they give you F naught, which this could be a typical problem, and they give you m, and you always know what g is, they could ask you to solve for the coefficient of sliding friction with that information. That's how you would do that. It would be equal to F divided by mg. All that said, they actually are not asking a question that is about that utilizes those details. They're asking more of a conceptual, qualitative question about the nature of friction. Which of the following statements explains why two forces exerted between objects are always going to be equal in magnitude? Why is that going to be the case? In the context of the frictional force that we were just talking about, that caused this constant speed motion. The gravity and the normal forces, they're referencing the third law pair, action-reaction pair. Action-reaction pairs, again, can be obvious sometimes, and a lot of times there's also times where it's not obvious whether it's a pair or not. Just know that if it's an action-reaction pair, they have to be equal in amount and magnitude, but opposite in direction. The gravitational force and the normal force, you might at first glance say that that's an action-reaction pair. It's actually not. The normal force comes from the ground pushing up on the box, and the box therefore puts a normal force down on the earth. That's an action-reaction pair. Normal force is an action-reaction pair with another normal force that's in opposite directions. They're both on the different objects. They both feel equal amounts of force in opposite directions. The gravity force, on the other hand, that pulls the block down is from the earth below, if you think of this as maybe a falling box. What is the action-reaction pair? This is the force on box from gravity. The reaction to that is actually the earth feels an upward force from the box, because they both pull on each other with an equal amount of force, but in opposite direction. I know we don't ever think about that, and quite honestly, it's pointless to consider it, but it's true that your weight is actually pulling the earth upwards all the time. It doesn't move the earth because it's just far too massive for that to even matter. But a gravity force is an action-reaction pair with another gravity force. In fact, gravity forces always come in pairs. That's what Newton's third law says. So this is not actually an action-reaction pair. The frictional force and the force exerted by the spring scale on the block. They originally described a spring scale that was pulling this. So they originally said that there was a block being pulled by some sort of scale that you're pulling on. The scale technically pulls the box to the right, and therefore the box pulls the scale to the left. Those are a action-reaction pair. The force between the scale and the box, because those are what's touching each other. But the action-reaction pair can't be between the spring and the frictional force down here, because those aren't even touching. Only the frictional force on the earth, the frictional force on the box. And which way does the earth feel that friction force? In the forward direction. There's a frictional force on earth. This is a frictional force. So when something's sliding, it's not just the sliding object that feels the force. Newton's third law says the earth must feel it too, in the opposite direction, right? In fact, if there was a piece of paper underneath here, and you slid this box really fast across the floor, and it slides over the paper, which way would it drag the paper? As it passes over the paper would end up getting kicked a little bit to the right, telling us that the frictional effect of that box sliding over the paper was actually a force to the right, right? That makes sense. That's an action-reaction pair. Frictional force and the scale, no. The normal force and the friction force, no. They have to be in opposite directions and equal in magnitude. So could that be an action-reaction pair? The normal force is up, the frictional force is back. Those aren't even in the same direction, so that already violates the rule, because an action-reaction pair have to be in opposite directions and equal in magnitude. So it has to be D. The frictional forces that the block and the surface exert on each other must be equal in magnitude, but opposite in direction. That's true. That's what I just talked about a moment ago. The frictional force that the block exerts on the surface and the surface exerts on the block, those must be the same. Those are an action-reaction pair. One's forward, the other one's back. One's felt by the block, one's felt by the ground. They're equal in magnitude, but opposite each other, opposite direction. D. Question 13. This is a good question, by the way. Question 13 says you have something that's kicked off, that's punched out of this little launcher, this ball. You've seen this from earlier in the year. And there's no friction, very little friction underneath here, where I'm pointing with my mouse. And that, therefore, when the launcher puts a forward force on the ball puts a backwards force on the launcher, because that's Newton's third law yet again. And therefore, if there's no friction here, that should cause the launcher to move leftward after it's kicking the ball to the right. So the launcher, if there's no friction, should technically slide to the left and fall down. The question is ultimately, where does it land? Well, if it was equal in mass, if the launcher and the ball had the same mass, then they'd both go in opposite directions and land in the same spot. I shouldn't say in the same spot, at the same distance. One would go and hit here, and the other one would go and hit here. That would be if they had the same mass. Why do I know that? Well, if they had the same mass, think about first, what tells us what important bit of information do we need to know in terms of what that distance is. Well, the distance they've moved sideways depends on the speed they have when they come off of this area where they're kicking off each other. What is their horizontal speed they have as they leave each other? Vx. Well, that speed depends on, I should say, the initial speed that they have coming off in the x direction depends on their acceleration and the time that they're accelerating for. It's just a fraction of a second. It's however long they're pushing on each other before they separate. But it's not 0 seconds. And so technically their accelerations, remember, is that they experience is due to the force that they feel between each other divided by their mass. The ball and the launcher both feel the same force because that's Newton's third law, yet again. That's why they go in opposite directions. However, they don't have the same mass. This says that the launcher launches a 0.3 kilogram ball while the launcher itself has a 0.6 kilogram mass. So the launcher is twice as massive as the ball. If they were the same mass, like I said, and the forces they feel are the same, their accelerations would be the same. Their accelerations during that fractions of seconds that they're pushing on each other is the same, and it's for the same amount of time because they're both pushing on each other for the same amount of time, right? Like if I'm on a skateboard and you're on a skateboard, and I push on you, and we both then roll away from each other, and we say, how long was my hand pushing on you? And you timed it. And you show me the amount of time on your watch, and then I show you the amount of time that was on my watch. They'd be the same amount of time. We're pushing on each other for the same amount of time. So since the time is the same, the accelerations will be the same, their velocities will be the same. And why would they land in the same spot? Because they're both going to be falling for the same amount of time as well, because they're falling from the same height. And remember also, horizontal launch speed does not affect how long they're in the air. However, the mass of the ball is actually half as massive as the launcher. So that means if the mass is half as much for the ball, the acceleration for the ball is twice as much. The ball experiences an acceleration during that fraction of a second where it's they're pushing on each other. The ball experiences an acceleration that's 2 times greater than the acceleration the launcher feels. So if the ball feels a 2 times greater acceleration for the same amount of time, then the velocity Vx for the ball would be 2 times as much. So that means, more correctly drawing this up, the ball has a launch velocity that's 2 times greater than the speed that the launcher has when it's kicked to the left. So if this happened to be a speed of 10 meters per second for the ball, this would be 5 meters per second for the launcher, because again, it's twice as massive. What does that translate into in terms of the distance? Not the same distance. If it has half the speed, then it will actually only go half the distance. How do I know that? Constant speed motion, right? Which is why these images show the ball equal distance horizontally apart, right? If this was 1 second snapshots and this horizontal distance between these two balls in all cases was 1 meter, and it's 1 second in between, then the horizontal speed is 1 meter per second, right? But remember that the horizontal speed is constant speed motion. So again, what would delta x be? Where if delta x is this called the range, if it's got half the speed, it's in the air for the same amount of time. Remember that horizontal speed, no matter how fast it is shot sideways, does not affect how long it takes to fall. They both fall for the same amount of time and land at the same moment. This ball and this one would be here, and this one would be here, and then boom and boom, they both land on the floor at the same moment. They both be at the same height at all moments. Time is the same. But again, if the speed, horizontal speed at launch of the launcher itself sideways is half as much, then delta x will be half as much. And that puts us to an answer of d/2. The launcher will fall off the platform and land a distance of half of this, right about right here, d/2. Right, moving to that. I like that question, by the way. A lot involved in that question. It's a good question. A student pulls a block over a rough surface with this scenario at play, an angled force. FP remains constant. I don't know why they're calling it FP. Oh, for pull, maybe. I don't know. Remains constant, so they're not changing the amount of force they're pulling in this direction. It could be a rope, for example, pulling constantly and consistently in this direction with the same amount of force. But the angle does change. They said as it slides, the angle actually increases. So as this block is moving, they start off with maybe a low angle, and then a little later, the angle has increased. Sliding along, the block is sliding along, but they've increased that angle. Not the magnitude, the force is the same in amount, but the angle has increased. What effect does that cause? Let's see. Will the force of friction change? Absolutely, the force of friction will change, because the force of friction down here depends on how much pressure there is in between those two spots. And remember that when you are providing an upward force, let me actually give myself some more room for that. When you are providing an upward force like this component of your lifting force reduces the amount of pressure underneath there, right? The amount of pressure underneath there is actually called the normal force. So when there's no force and it's just sitting there, the normal force is equal to mg. When there is a force now like this, and there's an upward component Fy, and this is still mg, the normal force is less. Let's say that this was Fn. In this case, now Fn is less, because this normal force plus this y component have to add up to mg. Because vertically it's in equilibrium. That's not ma, by the way, it's mg right there. So the upward component certainly does reduce the normal force. It reduces the amount of pressure that's underneath here. If there was a scale underneath it while it was moving sideways, the scale would give a less of a value as a result of increasing the angle, increasing the y component. The normal force would decrease. But remember, the normal force does have an effect on the friction force. Right? Frictional force is proportional to the normal force. So if the normal force decreases, the frictional force decreases. So will it cause the force of friction to increase? No. It will cause the force of friction to decrease. Nothing changes the weight of the block. So it's B. I mean, you just have to send the block to outer space, where g is less, and then it will weigh less. But that's not what we're talking about here. Next question. A satellite orbits Earth. The only force on the satellite is the gravitational force exerted by the Earth. Let's sketch this up. Here's Earth. Here's some satellite out there. The only force it feels, because it's in an orbit, is the gravitational force from the Earth. How does the satellite's acceleration compare to the gravitational field? So you should know, now you know, because I taught you this, and I actually told you to skip this question because you hadn't learned circular motion when you took this quiz. However, now you know that you can calculate g out at some distance r, where r goes from the center of the Earth out to that spot, by using this formula. You should know now that what I'm trying to teach you is that, remember, there's the inward force that the satellite feels is actually a centripetal force. And therefore, the force, the acceleration caused by that centripetal force is actually called the centripetal acceleration. AC is the centripetal acceleration. And the only thing out there, the only force providing that centripetal acceleration is gravity, G. So whatever G is out at that spot, that is the centripetal acceleration. If G out here happens to be, let's just say, 6 meters per second squared, and they said this is where we have a satellite in orbit, what is the centripetal acceleration of the satellite? It's 6. G is the acceleration it experiences out at that distance from Earth. And since that acceleration, since it's in a circular orbit, is a centripetal acceleration, G numerically is the centripetal acceleration. G and the centripetal acceleration are the same at any distance for any orbit. They said, how does the satellite's acceleration compare to the gravity field? This G is the gravity field, and acceleration is a centripetal acceleration. They're one and the same, right? As I was describing here, the gravitational field and the centripetal. And if I drew over here G, as a vector, I'd say G is a vector pointing down. It has a value of 6 meters per second squared. And then over here, I'd say draw the centripetal acceleration vector. It's down, and it has a value of 6 meters per second squared. So they're the same in magnitude. They're the same in direction. They're the same. They're the same acceleration. They're coming from the same force. They're the same acceleration. So the magnitudes are equal. D is correct. And they point in the same direction. C and D are the correct choices. An object is at rest on the ground. The object experiences a downward gravity force from the Earth. Which of the following predictions is correct about why the object does not accelerate downward? Well, we know that something doesn't accelerate downward when it's on the ground because the normal force cancels with its weight. They're equal in amount. The floor pushes up with a force equal to whatever it weighs, and there's no unbalanced amount of force. Wish it was so simple. They've tried to confuse it a bit. They said select two answers. B is correct. The normal force is exerted upward on the object from the ground with the same magnitude as the gravity force down on the object. Boy, that part's simple. Yep. Let's pick that one, B. But they said select two answers. Then they start going into bonded molecules. I don't know why they do this stuff, but, you know, it's their choice. So technically, bonded molecules just mean molecules that are bound together. In a molecular way, right? You can have atoms that form molecules, and you have molecules that come together and can. This is all electrical. They electrically and magnetically stick together to form compounds, and so complex molecules can be formed with compounds, and so on and so forth. When they're kind of stuck together magnetically, they call that bonded. They're bonded together, and they're saying that the reason that the block doesn't fall, why doesn't it accelerate downward when it's on the floor, is because the bonded molecules of the object, what the molecules of the object is made of, are repelled upward. That sounds about right, right? The box feels an upward force. They're repelled upward with the same magnitude as the gravitational force downward. Yep. They feel an upward repelling force from the ground equal to what the Earth is pulling downward on them with. That repelling force, believe it or not, is electrical. I wish we could talk about that, but we're not going to be. I'm not going to be teaching you about electricity. But if you're looking at the ground, you know, the ground is made of atoms, of course, and atoms have electrons. These are all electrons around the outside of an atom. This is considered an atom. Plus, in the center would be the nucleus. So technically, the ground, the surface of the ground, the outermost part of the ground is negative. It's not like I'm drawing it, but the outer edge of all atoms is negative. And technically, when you bring another object and lay it on the ground, the outer edge of that is also negative. And since negative and negative repel, since they're electrically opposite, that repelling force prevents the block from passing through the ground like a ghost. So technically, the concept of being solid is all illusionary. It's all an illusion. A lot of the world is illusionary. There's no real contact with anything. You're actually hovering over everything that you sit on at a very, very, very small microscopic scale, but it's still technically true. And the force, the normal force from a macroscopic scale, we call it the normal force. From a microscopic scale, we describe the normal force as what I've said here. The normal force is technically the electrons in one object repelling the electrons in the other object. You try to slam your hand on a desk. Why does your hand not go through the desk? For this reason. The electrons on your hand, when they get really close to the when they get really close, because like gravity, these forces get really strong when the distance gets small, become such a strong force that the repulsive force will stop the motion of the thing that's coming in, like your hand, prevent your hand from just passing through it. So A and B are the correct answers. A student uses an electronic force sensor to study how much force the student's finger can apply to a specific location. The student uses one finger to apply a force on the sensor. All right, so you have a sensor that measures force, and you take your finger and you push on the sensor. The data collected that comes out of the sensor for two trials is shown. For trial number 1, the force sensor suggests that it did not feel anything. For trial number 2, the force sensor suggests that you were pushing on it with a force of 8.5 newtons with your finger. During which trial, if any, does the student's finger experience the greatest electromagnetic force? Why are they talking about electromagnetic force? It's actually what I was describing here. you wouldn't know that at this point. And since we're not even going to do electricity this year anymore, I'll never talk about that. But this force that I was referring to is technically electromagnetic. It has to do with electrons. And anytime there's electrical charges that move, these actually are not perfectly stationary. Electrons technically orbit around the nucleus, and that causes a magnetic field. So every atom actually has magnetism that surrounds it, and those fields are called electromagnetic fields. But they can push or pull on other objects, as I've described here. And so that's why they've called it an electromagnetic force. You didn't really need to know that, but I'm surprised they threw that in there. Either way, during which trial, if any, does the student's finger experience the greatest electromagnetic force? Well, during trial 1, if the force sensor didn't feel anything, that's because you weren't pushing it, and therefore your finger didn't feel anything either. During trial 2, the force sensor felt 8.5 newtons, and therefore your finger felt 8.5 newtons because that's Newton's third law. So during which time was it the greatest force felt by your finger? I guess they're trying to assess, does the student recognize that if the force sensor feels something, then your finger feels something, because this question's about what your finger feels? I suppose so. It's Newton's third law. During trial 2, your finger feels the greatest force, certainly greater than 0 during trial 1. Trial 2, because the singer's finger applied the, yep, trial 2, B. All right, moving on to 18. Oh, I like this little toy. I have one similar. You've seen it in class. A toy-powered car. A toy car has a battery-powered fan attached to it such that the fan creates a constant force, right? The blades are spinning. They push the air backwards. Newton's third law says the air must therefore push the blades forward. That causes this to move forward. With a constant force, since the spinning speed of the fan is constant. And it's exerted on the car so that it's propelled forward in the opposite direction from which the fan blows air. That makes sense. The car has a carriage that allows students to attach objects of different masses in here. The fan has only one speed setting. Great. All frictional forces are considered negligible. Great. Which of the following procedures could be used to determine how the mass of the fan car is affected by the acceleration of the system? In fact, this is what we just did recently with the modified Atwood machine. It's Newton's second law lab I did with you on Pivot Interactive was exactly that. Let's measure the effect of mass for that car that was on top has on the acceleration when the hanging amount of mass was constant throughout the experiment. Measure the mass of the system using a balance, activate the fan, and measure the distance traveled, which we did in the Pivot Interactive, and the known time, which we did in the Pivot Interactive, so that we could calculate the acceleration, which you might recall comes from delta x equals 1/2 at squared. And therefore you can solve for an acceleration in these questions by knowing what is the distance and what is the time. 2 delta x over t squared is what you get when you solve for acceleration. But just meter stick measurements and stopwatch measurements can certainly give you enough information to calculate A. Good, because the question was, which of the following procedures could be used to determine how the mass that you stick in here is how that amount of mass affects the acceleration? Well, I think this sounds good, right? Measure a distance, time it, and repeat the experiment for several trials, each time adding some extra mass. That will definitely do it, because you can measure the amount of extra mass each time that you put in. Each time you can measure the new time and distance and calculate the acceleration. And you could certainly do a plot of acceleration versus mass, which I might ask you, do you remember what it looks like graphically? Newton's first law suggests that it should graphically look like inversely proportional. You got it. They didn't ask that, but they could have. A sounds good. Let's use A. A couple more. Now this one actually I think was the most incorrect out of all the AP students this year. This one problem here was answered incorrectly more than any other question. Let's look at it for sure. An object is moving along at 2 meters per second and collides with an object that's just sitting there. It appears to be twice as massive as this one. He's just sitting there and he comes over and he smacks into him. All right. At time t equals 0 seconds, he's moving along with a speed of 2 meters per second. All right. Toward object y, object x, object y, okay. He has 2 times the mass, okay. He's 8 meters away, okay. Blah, blah, blah. Where's the important information? Both objects are on the horizontal surface. We see that, where the frictional forces may be considered negligible. Thanks. Which of the following pairs of force diagrams represents the forces exerted on object X and object Y? Now we're getting somewhere. Which of these free body diagrams is best representative of the forces they feel, not in this image, but when they collide? Because they happen to say at t equals 4 seconds. And since he's moving at a speed of 2 meters per second, after a time of 4 seconds, he'll have moved 8 meters, which indicates where will he be? He'll be banging into him. They know that there's going to be some students that are going to just take this problem for face value and say, all right, you want 2 free body diagrams for them right in this picture as they are shown? A. Not correct. Some amount of students will pick up on the idea that they said 4 seconds later and say, oh, it's when they are in contact with each other, once they're banging into each other. First off, he weighs twice as much. He's twice as massive, right? So the upward and downward vectors for his free body diagram definitely have to be longer than his. Technically, they have to be twice as long. 1 block versus 2 blocks. Looks good. 1 block versus 2 blocks. Looks good. 1 block versus 2 blocks looks good. 1 block versus 2 blocks looks good. That doesn't help us very much. They all have that correct. So now we're really interested in how about the other way, X and Y, X-axis and that, right and left. Well, when he smashes into him, the 2M guy will feel a force to the right. Missing. Can't be that one. Okay. He feels a force to the right. From who? From box X. That sounds right. He'll feel a rightward force from X. He'll feel what will he feel? What will this guy feel? When he, boom, bangs into him, if this is you running into a door, this is the door, and this is you, which way does your head feel the force? Bam, you smash into it. It's a leftward force. The door might get dented, which indicates it was a rightward force on the door. Your head feels a backwards force, and we know that because you would slow down right away. And a backwards direction force while moving to the right would slow you down. Sounds about right. He's going to feel a leftward force. Will it be the same amount, though? And this is where the students of mine had varied in their opinion. Do remember, Newton's third law says, in all cases, forces come in pairs. They will be equal in amount, opposite in direction. Looks good. Equal in amount, 2, 2, 1, 1. He's 2 times more heavier. That looks good. That's good. What was the most commonly incorrect chosen answer? This one, for you guys. Because you thought, which I get it, that since he's smaller and more massive, he's going to feel a larger force than him. Just like a lot of students will think that the Earth feels more pulling force towards the sun, and the sun feels less pulling force towards the Earth. Not correct. Newton's third law suggests they're the same amount in magnitude, but equal opposite rather in direction. Earth doesn't move as much because it's so much more massive. A is inversely proportional to m, just like we just talked about in the last question. So why does he move his motion changes so much more dramatically? Because his light mass. He's more responsive to that force created when they run into each other. He's got more inertia. He's less responsive to that force, and he won't move as much. Most common wrong answer, C. Correct answer, B. What did D look like? I'm trying to understand this. Let's see, what is FY? F. No, what's different? I didn't quite see what was different, to be honest with you. FY, that looks correct. Oh, I didn't pick up on that. This guy's only one unit long. This guy's 2. Yeah, it got to be the same amount of force left and right. He feels it to the right, he feels it to the left, but in an equal amount, equal magnitude. All right, moving on. We're almost there. Number 20. The student sets up an experiment to determine the inertial mass of a car. Well, to determine the mass, the inertial mass is really relating to how much resistance it provides when you're trying to move it sideways, perpendicular to gravity, gravity straight down. So a sideways force, and when you observe the motion of something when you're trying to push it sideways, gives you a good sense of its inertia. Gravitational mass, on the other hand, is relating to how much it might move in the downward direction due to the force of gravity. They're actually equivalent, gravitational mass and inertial mass. All experiments, whether they're sideways or vertical, yield the same value for an object, m. You don't do an experiment with a cup that indicates, when you do a gravity vertical experiment, it indicates the cup has a mass of 1 kilogram. And then when you do the sideways experiment with the cup, it indicates the mass of the cup is 1.2 kilograms. You don't get them conflicting results. Experiments in all directions indicate that the gravitational mass and the inertial mass have the same numerical value. Just FYI. They're asking, what process would you follow to determine the inertial mass here? Student sets up an experiment, student blah, 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 has a scale, a meter stick, and a stopwatch, uses a spring scale to pull the cart along a horizontal surface such that the reading on the spring scale is always constant. That means it's moving at a constant speed. Actually, that doesn't necessarily mean that. Could be accelerating and still be constant. All frictional forces are negligible, okay? In addition to the spring scale reading, which two of the following quantities could the student measure with the available equipment and then use this to determine the inertial mass? Oh, it's still there. To determine the inertial mass, as long as we can measure acceleration and force, we can work out mass. Yep. You can say F net equals ma if you'd like to start there, and then say m will be the net force divided by the acceleration. Right? So the net force. In fact, let me read this again. I see, because it is accelerating, because they did say that the frictional forces are negligible. So that means this force that he's providing is causing it to actually accelerate to the right, because there's no leftward frictional forces. Either way, that means that the net force, if this is the free body diagram for that thing that he's pulling, these cancel, and the net force, this is the net force. There's no backward frictional force, right? So reading the value of the spring scale is the net force. And then the acceleration is measured, of course, by just doing stopwatch and meter stick, right? Just what they said, stopwatch and meter stick. You can use, 1/2 AT squared. Just wrote that down on the top here. But you do it up here, delta x equals 1/2 AT squared. And again, solve for A. You guys have done this a number of times in different labs. You can solve for the acceleration just by stopwatch, delta x, meter stick for delta x, stopwatch for t. So what do they need to do? They need to measure the total distance. No. Oh, this is a select 2. So what things do they need to measure to determine this inertial mass? Measure the net force, which they already said that he would use the scale. The only other thing they have to do is measure the total distance and measure the time. They could then calculate the acceleration doing this, and then plug it here, and now they've got the net force from the scale, they got the acceleration, calculate m. So the answers would have been A and D. All right, and last but not least, oh, I love this question. 2 people standing on a skateboard. Let's see. In order to get the student skateboard system to accelerate, student X says student Y should just apply a force on student X. So in order to get them, they're not moving, they're just standing there. And student X says to her, hey, let's get moving, just push me. Student Y should push student X. That's what student X believes, and that will get them moving. Which of the following statements is true regarding this claim made by student X? The claim is correct. Well, remember what we said in the beginning. System, what's the system? The skateboard and the 2 people. Anything internal, which is any forces, including the normal force at their feet, the normal force felt by the skateboard down by their feet, the normal force, again, up on their feet from the skateboard, and any internal forces they might apply to each other are all internal forces. And those forces cannot cause translational motion. You can certainly make her fall over, but when she falls over, her feet would probably kick the skateboard to the right as she fell to the left, making you think that that worked. That's not what we're talking about. That would be because her foot technically, as she was falling, pushed off to the right. Although actually, I think that's interesting. Would that if how well I'm trying to think of somebody like their arms are waving as they're falling, and then they kick. I have to think about that. That's interesting. Maybe not. I don't know. That's an interesting question. Anyways, the answer certainly is no. Just her pushing here, or her pushing her, just a general push. If they just pushed each other relatively lightly, or even a little hard, they're not going to. The skateboard's not going to move. Why? Because of the action reaction. Her hand pushing on her body to the right will cause her body to push on her hand in that same moment to the left. Those forces will cancel. There'll be no net force generated as a result of that, and therefore it won't move. The claim is incorrect because both students are internal to the student's skateboard system. The internal forces within the system may not cause the system to accelerate. D is your correct answer. And that finally finishes my review. It was a long one, but it is what it is. We need to get through those, and I hope you take the time to review it. I don't know how long that was. It was probably around an hour on both. It's been an hour on both, so it's about 2 hours. So hopefully you will. I mean, I don't mind doing it. I'm not saying I mind it, but I give you all the details that you need, and all of the hopefully the conceptual understanding is the most important part. So if you guys hopefully found that useful, then that's a success. I will eventually be asking you to, well, if you're watching this, this will have already happened, so I shouldn't say that, but I'm just talking out loud that I will be asking you guys to review this with your own problems from AP Classroom for that quiz. And so I'm certain it will be helpful to you guys. And I guess that ends it. All right, signing off, guys. See you later. Till the next time.